right? Yeah, so we set that equation to equal 0 because, well, we want to know, typically, we're looking for the actual zeros. And then we solve. What values of x will allow me to have my x values here to be 0? Um, well, be that as it may, I'd like you to consider the idea that um, instead of saying, will it equal a 0, think about it in a different way. I have this line, this horizontal line. And if you remember your lessons from grade 9 and 10, a horizontal line has a slope of 0, and in this particular case, my y-intercept is 0. So literally, the equation of my line is slope of 0, x, plus a y-intercept of 0, right? It's 0. It's just a line. So when I say, will x squared minus 8x plus 32 equal 0? Sorry, I don't even need 32. Let's just pretend that's a 0, okay? I don't need that. I just changed my equation just to make it match the formula, the parabola. Will f of x ever equal 0? Is sort of like saying, will f of x ever equal this horizontal line? You see how that could be one and the same? Maybe? I'd like you to consider that idea is because today we're looking at what would happen when we are let me backtrack. The reason I want you to consider that idea is because if you see that you are simply looking for the times when this parabola intersects with a horizontal line, today's lesson is literally the same idea with the parabola, but I'm looking for an intersection with not a horizontal line, but just a regular line with a slope. I am simply looking for the intercepts, so intersection points, just as you were looking for the intersection points here. It might seem a little bit weird. Maybe let me go through the handout more in detail, and this idea might sort of come together a little bit better. Okay, so if you have it in front of you, would you please take out the 1.7 handout? I will get mine out as well, and away we go. Yes, I will post it. I think I have the classroom posting already up, but you know what, Helen, since you're asking, I'm gonna just double check to see if it's already up there. I'm usually pretty punctual with this stuff, with the recordings, at least the day of, so you should see it. Let's see, 1.7. Yeah, it's already up there. Um, But just because you're part of this, maybe I'll upload a second one and just set it for your class specifically. Okay, let's do this. So 1.7, linear quadratic systems. Everything that we are doing today is no different than what you've always been doing, but I'm just going to simply frame it a little bit differently. So here's my x-axis, and I'm going to use, let's say, red. My first, let's pretend here's my parabola, and because we're dealing with a quadratic equation, let's call this function q of x. Okay, Zoe, I will mark you present in just a bit. Let me just finish my thought process here. And then I have with me a what's the line? So you could already imagine, so this, let's pretend this is line, so straight line, linear, L of x. Oh, there it is. Okay. You can already imagine when we are looking at a system that involves a quadratic and a linear, there's going to be one of three different possibilities. These two functions may never cross each other, may never touch each other, may never occupy the same space. Or you could imagine this line might be right there and touch the parabola at exactly one space. Or it might be up here where it touches the parabola at two different places. Right? Isn't that very similar? Like, let's bring this aside. Let's pretend I had with me, this parabola. Here is a parabola touching the x-axis two places. Here's a parabola touching the x-axis at one place. And here's an parabola that does not touch the x-axis at all. This is why I'm asking you to consider the x-axis as a vertical line, like a linear function, right? And do the same thing as I've always been doing. By that I mean, take a look. Let me put this little note here, okay? Let's see. When q of x is set to equal L of x, okay, the result in this case should be what we call impossible, okay, to solve, because there is no place, I guess, in no point that q of x and L of x share, right? They don't overlap. They don't share any common space in this entire world, I guess. Right? So if this is what it looks like visually, there must be a way we can identify that mathematically as well, without any images, without any graphs. It should also be very, very obvious mathematically. So pause here for a second. I'm going to ask a random question. Where in your previous practice, where in your previous math, have you seen a situation where you're not able to solve further? When have you ever come across a situation when the math was impossible to solve? True, Ian, true. What part in radicals? When in radicals were you not able to go any further? By radicals, he's talking about this stuff. You know how we had like, 16 times like something like that, okay, or 16 plus 9 or something like that. The decimals, not necessarily. There was a situation with a square root where you were no longer able to continue further. What was the special condition? Anyone? Going once, going twice. When it doesn't simplify to be a perfect square, simplify to be a perfect square. Oh, you're talking about when we have like 11 and you can't simplify further. No, I'm talking about like when you actually there was no such possible number period, right? And I think yeah, Harriet and Kinda's got it when the square root portion gives me a negative. Let's take an example, okay? So I have created with me, let's use red, some examples where the equation is very close to the drawing that I wrote. So my vertex is about 4, 4. So how about I do this? Okay, so that's my quadratic. And my linear, L of x, I'm going to say it's just a slope of 1 just to make my life easier, but the y-intercept looks like a 3 maybe. Bam. So my question again is, when is q of x and L of x going to occupy the same space in this universe, same space in this grid? Okay? And again, instead of writing q of x and L of x, because that's just symbols, instead of q of x, I can write the entire equation and make that equal to L of x, but written as the entire equation. And the rest is, I'm just going to simplify. All right? When will, so let me expand this, x minus 4 times x minus 4 plus the 4 equals x minus 3. Now let's continue further. When you have a polynomial like this, I see some common terms. The x terms will group together. I have constants. They will group together. X squared minus x, that's negative 9x. 16 plus 4 is a 20. Minus 3, so that's plus 3 plus 3, that's a 23. Great. So at this point, it was a little weird, but here I think it should be familiar to you. I have a polynomial, a trinomial, it equals 0. If we want to know what values of x makes the y value a 0, which makes this equation true, there's a couple ways we can do it. We can factor, or we can do quadratic formula. Is this factorable? In other words, is there a number that multiplies, two numbers that multiplies 23, but it will also add to a negative 9? The answer is a resounding no. 23 is actually a prime number. The only ones that we can do is 1 and 23, and that will never add to a negative 9. So, since I can't factor it, I am going to resort to the quadratic formula. And remember, I always ask you, when you're doing the quadratic formula, please check this first. It can save you a lot of hassle. Here's my b value, here's my c value, and of course here's my a value, which is a 1. B squared is negative 9 squared, 81, positive, minus 4 times 1 times 23. That's an 81 minus 92, which gives me negative 11. Oh, there it is. There are no possible x's that will make this true, which means there are no possible x's that will make that true, which means there are no possible x's where these two are ever going to occupy the same space in this grid. Okay? So I'm thinking from here to here is something you've seen before, so that shouldn't be new. It's just this part that I wanted you to consider in our minds on. Instead of setting the parabola to 0, I'm not interested in whether the parabola is going to cross the line y equals 0. I'm not interested in that. I am interested if the parabola is going to cross this line, which happens to be y equals x minus 3. That's the whole goal. And you'll see some examples, some question examples we're going to do later on. But if you understand this portion and understand how I'm setting one function to equal another function and then simplifying it, that's 1.7. Okay. Any questions before I move to the second example? Because I'm going to go pretty fast then. No? Okay, so I'm going to move this down. So it's the exact same function with the x and the x-intercept and y-intercept, but the x-intercept, the linear function is going to touch the parabola at exactly one location. Another way we can say that is the linear function is tangent to the parabola. Okay, so let me erase this. All right, so I'm going to just make a quick note instead. All right, so if you were to do the same as above, the square root b squared minus 4ac would equal, what does that have to be if you want this to only have one answer? quick recap from chapter 1.5. That was just the last lesson. Uh, Someone who hasn't given anything? Kinda? Thank you. It has to be a zero if I want this to be the only possibility, if I want only one possible answer. Okay, so that must equal 0. Okay, so it giving only one possibility. I'll stop again. Any questions? No? Okay. Well, again, for the two sections then, it's the same idea. I'm going to move my blue. It's going to cross the parabola at two different locations. So if you do the same as above, the b squared minus 4ac would equal a positive number giving positive number, which means the plus minus of b squared minus 4ac will form two possible answers. Okay. The b squared minus 4ac portion would equal a positive, so the square root, the plus minus portion, will give you two answers. So in just a minute, we're going to see this in action, where you can say, oh, so I know for sure it's not versus I know for sure it will intersect. Yeah, I'm hoping that it's not simply a matter of memorizing for you, that you are able to understand that up until now, you have been looking for when the when the y value is a 0, in other words, where the x-intercepts are, but that you're basically checking to see when it crosses a horizontal line. And we're doing the exact same thing, but instead of setting it as a horizontal line, I'm just giving a linear. Okay, clearing in 3, 2, 1. All right. So this is just a bunch of steps that you can follow if you are still not quite grasping the broad idea of it. But let's do this. Okay, so the question is very straightforward. This is probably a knowledge or just a straight up application question. Determine the number of points of intersections of the quadratic and linear functions. So determine the number of points. I'm not even interested in the actual intersections. I want to know how many there are. So don't be confused by what the question is saying. Interpret this as, oh, you want the points of intersections? The points of intersection is just like saying, when does it overlap? If it's overlapping, that means at some point, this function and that function are going to be exactly the same as each other, the same position, the same point. Okay? Points of intersection is a mathematical term, I guess, but when you think about it logically, it just means when do these functions overlap each other? So I'm going to set them to equal 3x squared plus 12x plus 14 will therefore be set to equal 2x minus 8. This in itself is too hard to solve, so I am going to simplify it by grouping the like terms together. Minus 2x, this becomes 10x. Plus 8, this becomes plus 22. And from here, it should look familiar. Do you want to factor? As soon as I see these combinations of numbers, I don't want to factor. In my head, I'm like, do I really want to find two numbers that multiply to 66 but will still add to a 10? Too much work. So I'm thinking you might want to resort to quadratic formula as well. And as well, always, before you do anything else, you may want to check this. b squared is 10 squared. 4 times a times c is square root of 100 minus 12, 22, 240, 240, 240, 264. I already see that the square root portion is going to be a negative. Another way for me to motivate you to want to go this route, to learn this math, is because if you are looking for the points of intersection in grade 9 and even in grade 10, you may have just drawn this and crossed your fingers in hopes that your drawing is very accurate. You'd be like, oh, that looks like a 2, 2. That's the intersection. But when we start doing parabolas, no one's got time to draw. Okay? So this is by far the faster way. You do not want to sketch graphs just to try to get an intersection. Okay, okay, Gemma, I'm going to do the attendance in just a second. Don't worry about it. For everyone else, using this as a template, I'd like you to try number 2. I'm going to go through the attendance again, just cross-checking with how many participants are here. Please give it a shot. We will take up the answers in, I'm going to say you can do this in less than 5 minutes. So I'll give you 5. All right, let's see. Connor's here. Zane T is here. Thank you. Awesome. Whatever. I'll just say that you weren't late. Uh, Gemma, I gotta fix you. Connor is absent. Gemma is not absent. Zoe is here. Monad is accounted for. That's totally fine. And then F1. Kiara made it. Kiara, you're here, right? Kiara, you gotta help me out. Show me that you're at least present. And Jonah is here. Great. Thank you for making it. Okay, so everyone is here. If you got here a little late, I am in the process of recording, so um, you can check that out in just a bit. Where do you post the recordings? If you go back to the post where you found my handout, you will see that as time goes on, I've added a Google link. You can just click that and watch it. If you don't like watching it from the preview screen, just click on the link and go to YouTube. It'll take you to the YouTube site. All right, let's do this. As per usual, I want to see, it says determine the intersection points, which sort of gives it away that there are going to be intersection points. Again, that's another way of saying where is the overlap? Where are they touching each other? In other words, when are they ever going to occupy the same place? When are they ever going to equal each other? In the name of simplifying, I'm going to expand this and group them, giving me x squared plus 4x plus 4x. 16 minus 43, 33, 20, negative 27 minus 5, negative 32. Okay. If you wanted to go quadratic formula, first thing you want to do is check this. I also noticed that this can be factored, but let's say this was like a test question and you're so, tunnel visioned and you're so worried that you don't know or you're not confident or you're scared that you're going to be factoring this wrong and you want to use quadratic formula. Let's first check. E squared minus 4ac. E squared is negative 4 squared, that's 16. 4 times a times negative 32. Oof, that's 16 plus 128, which means 144. Oh, that gives me plus minus 12. Great. So I know that this is going to work. Negative b plus minus the discriminant portion over 2a. Negative 4 plus minus 12 over 2 times a, which is 2. If you're not quite sure what the heck just happened, I solved the discriminant already. It's a plus minus 2. So instead of writing the entire discriminant again, I'm just going to replace it with the plus minus 12. Sorry, not 2. Plus minus 12. So x is going to equal 4 plus 12 over 2 or 4 minus 12 over 2. X is 8 or negative 4. So there are two intersection points. What are those intersection points? We have the x's. Where are you going to find the y's?
Plug it in.
Right on. Which one do you want to plug it in? F of x or g of x?
Whichever is easier. I'd say g of x.
Yeah. Remember, let me recap what you just found in case you're doing math without understanding why. When x is an 8 or when x is a negative 4, it makes this equation true. That is when we get the 0. If it makes this blue equation a 0, that means it makes this equation truth. In other words, this left side is going to equal right side, which means it makes this left side equal the right side, which makes these two functions equal each other. Okay, that's what 8 and the negative 4 is. The 8 and the negative 4 is when these two are equal to each other. So let's plug it in. Whether I put it into here or I plug it into here, you're going to get the same answer because they are, yay, equal to each other. So as Ian was saying, I am going to choose the answer or choose the function that is easier. And I think the linear is going to be easier. If you don't believe me, you can plug it into f of 8 as well to see if you get the same answer. So that's negative 4 times 8, negative 32 plus 5, and that's negative 27. So one of the intersection points is 8, negative 27. Let's plug in the negative 4 plus 5. So we have 16 plus 5, which is 21. So the other point of intersection is that. So I don't quite know, just from looking at it, where everything might be, but I do know that 8, negative 27, somewhere here, is one of the intersection points. So that's 8, negative 27. You don't have to sketch it, by the way. Negative 4, 21, somewhere here, is an intersection point, and I know that's where the vertical line or the linear function is. And with that, I know that the parabola is negative 4 all the way down. The parabola is something like that. That's a really not nice looking parabola. I'm just drawing this to give you a better visual of what it is that we actually calculated just from using numbers. This is, the red is f of x, and the black is g of x. And we were able to find the intersection point. Any questions?
Where are the textbook questions for this? What page?
It should be on your handout, but specifically page 67, numbers 1, 3, 5, 10, and 11 are what I assigned on that sheet. Okay. Oh boy. All right. I have just over 20 minutes for this parent function thing. I'm not going to go into details of all the little things I want you to notice as we go. I'm just going to give you the bare bones. I'd like you to copy it and just be aware of the fact that these are some of the functions you are going to be encountering sometime in the near future. Okay? So I'm going to close this. I'm going to clear this for a second. And I'm going to share our 2.0 intro parent functions page. I hope you can see it. Okay. So, context. In grade 9, you learned all about the straight line. You learned about how we can move this thing up and down, right? We learned about how slope controls the direction in which we are moving, rise over run, blah, 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 blah. Once we got the hang of that, in grade 10, sorry, grade 9 was straight lines. In grade 10, you learned about the parabola. You learned about how we can move it up, how we can move it down, how we can move it left and right, how we can stretch it. So just like how we can move the line up or down, we learned how to move the parabola up or down. We also learned how to move the parabola left or right. We also learned how to stretch the parabola or compress the parabola, so on and so forth. In grade 11, you're going to be looking at, I'm going to say, like 7 new functions. But once I get a chance, I'm going to show you that the system that we use for the straight line and the parabola are exactly the same. They're actually the same thing, but we just described it differently. And if you get the hang of being transforming parabolas from grade 10, you are going to use that same knowledge to transform a graph that looks like this, graph that looks like this. Okay? You're going to transform graphs that look like this. You're going to transform graphs that look like this. You're going to transform graphs that look like this. 1, 2, 3, 4, 5. Is there another graph I'm forgetting? Anyways, you get the point. So before we actually get to the transforming portion, I just want you to know what these points are. See if you can catch any patterning, and so that you won't feel intimidated by it. Okay, that's my purpose for today. So linear functions. I'm going to get us to do some accuracy points. I'm going to call them APs from now on. All right. And from there, you're going to use that to draw your parent function. And from there, we can learn to transform them. Take a look. If x is a 0, my y value would be a 0. But if x is a 1, what would my y value be? Come on, people. Show me that you're following.
1.
1. Thanks. Okay, Ian, you can't do it anymore. You're taking up all the opportunities. If x equals -1, someone else. Louisa?
-1.
Yeah, there you go. Okay, and so we have 0, 0, we have 1, 1, we have -1, -1. I'm pretty sure you will believe me when I say, hey, this is my linear function. Right? And if I were to transform this, like for example, you know what? I'm going to say that. You might, let's just leave it at that. This is my linear function. Very straightforward. Y equals x. Let's go into our next one, which is very familiar to you. Y equals x squared. Please turn the page to number 3. Let's do number 3 first. For the parabola, my accuracy points were, do you remember when you were asked to graph this? Right? You did so many transformations in grade 10 that you should have memorized at least 5 of the points that you start with when you're drawing the parent function of a parabola. Who's on my list? Mirdok, what are those 5 points that you were asked to memorize? Going once, going twice. Nathan. Oh, yeah, Mirdok.
I feel like one of them is 0, 0, and if it's
Yes,
not, then I don't remember the rest
it
of
is
them.
0, 0. And then, what was the
Oh,
next point?
you're asking me to remember the grade 10. I barely remember anything from that time.
I don't think it's a tall order. Come on, look at what I just drew.
Oh,
You should have transformed so many of these that it should be like bam, 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 bam. I know the 5 like the top of my head.
okay. So, are you talking about the points you made?
Yes,
Oh, okay. Then 1 and 1, and
right. So
then
when x equals 1, 1 squared is 1. Good. When x equals a 2, 2 squared is?
2 squared is 4.
Good. Go backwards. If it's a negative 1, then?
It's a -1.
No. Negative 1 times
Neg-
negative 1.
oh, it's -1 times -1 is 1.
Yes. And negative 2 times itself?
Is 4.
Yeah. So this is what I mean by accuracy points. Even without actually calculating it, I'm hoping that you graphed so many of these that bam, 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 you can draw the parent function just by memorization off the top of your head. I hope. Okay? And when you transformed it, let's say you did x squared plus 4, what happened? 1, 2, 3, 4. That's where it went. And if that's the vertex, it's bam, 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 bam. Right? It's grade 10 stuff. Hopefully you remember it. It's the same system, but I'm going to give you some new parent functions. All right, let's go to number 2. This is one of the first ones that you have not yet seen, but that's okay. Number 2. All right. Absolute value function. Anyone here know what the absolute value means? Nathan, do you know what absolute value means?
No.
That's okay. How about Noah? Do you know what absolute value means?
I don't think so.
That's okay. Okay. You know what? For the people who don't know, you're actually sort of in the. It's better that you don't know because a lot of people actually memorize the wrong definition. Some people will be like, "Oh, absolute value is," right? Um, just take whatever numbers inside and change whatever it is to the positive value. That's what they think it is, right? And I think it's not their fault. A lot of teachers sort of teach in that way too. But I don't want you to think about it that way. I like you to think about it like this. Absolute value is how far away from 0 is the value. You might not have any idea what I mean by that, so let me try to hash it out. Okay, so the absolute value of -5, I'm going to draw a number line. That's my 0. 5. Patrick, how far away from 0 is the number 5? Going once, going twice. I don't have much time. Simon, what about
5.
you? Oh, what's it again?
5?
Yeah, just 5, right? The distance is 5. How about -5? How far away from 0 is -5?
-5?
No, just the value. How far?
Okay.
How many steps away?
5.
5. This is what absolute value means. how far away from 0 is it? So if I have negative 121, don't be like, oh, no, just get rid of the negative. Don't think like that. Take the negative 21 and say, how far away from 0 is it? And you'll say, oh, it's 121 units away from 0. I know it sounds like just minor details, potato, potato, but when you get to grade 12, that idea might be a little bit helpful in understanding a concept there. All right? So, if the x value is a 0, or the y value is going to be 0, if the x value is a 1, Saima, how far away from 0 is 1?
1,
1. Good. How far away from 0 is 2?
2,
Good. How far away from 0 is negative 1?
1,
Good. And how far away from 0 is negative 2?
2.
Good. Okay, so we've got 0, 0, 1, 1, 2, 2, and negative 1, positive 1, negative 2, positive 1. If we keep going, you'll get the absolute value that looks like that. This is the parent function if you ever see an absolute value. From here, I'll give you an example. What if I gave you a new function that is here? Let's do parallel. If this was x squared and I said it transforms into x minus 3 squared, Waylon, what does this mean when the x value is subtracted by 3?
Are we still talking about the absolute value?
No, we're just, if I did the parabola, what does that mean?
It's shifted to. Is it a translation?
Yes, it is.
I can't remember if it's to the left or right though.
It's going to be to the right. It's a negative. It looks like a negative. It's going to be positive. The same thing is here. My original is this, but I transformed it to that. So what does that mean? This parent function is going to move to the right by 3. This is why I say if you understand your transformations from grade 10, the next chapter, chapter 2, you've already learned it. So don't think it's a waste of time. Think about transformations of the parabola because you're going to be applying that same idea, same system into all of these parent functions. Okay? You'll get some more examples later. I'm going to rush it because I have less than 10 minutes with you. Let's move to number 4, the square root function. All right, square root. You're going to see some interesting similarities of the square root with the parabola. Okay? So accuracy points. Let's do this. Accuracy points. Oh, I want black. Thank you. X can't be a negative number. But when x is a 0, y is a 0. When x is a 1, square root of 1 is 1. I could put 2 here, but I don't want to deal with a square root of 2. That's like 1.41 blah, 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 blah. I don't want that. Someone that I'm going to call on, is there a better value of x that I can use to help map this out? Zane T, what about you? Instead of 2, is there a better number that I could use? Going once, going twice. Sorry, I don't mean to rush. Louis, what about you? What do you think? A number that you can square root nicely. I'll go back up the list. Aiden? No?
Yeah, sorry, could you repeat the question? Sorry.
Oh yeah, no, it's okay. Helen's got it. What x value that can I put in so that I don't have to deal with any exponents or any kind of decimals for the y value? Helen is like, hey, if you put a 4 there, square root of 4 is 2. What's another number?
Are you asking me?
Yeah, sure. Aiden?
Okay.
So a number that when I square root it, it won't be a decimal.
Oh, okay, 9.
Yeah, 9. Square root of 9 is a 3, and I'm going to go one step further. 16 gives me a 4. Do you see something a little interesting, 4, 2 with this one. It's a 9, 3, and then 16, 4 is like way over there. What does that sort of look like? Amina, what do you think?
Um,
You see it? The square root is actually a parabola, the regular square function, on its side. And yes, you might imagine there is a relationship between two. They're called inverses, but you don't have to worry about that now. There's an actual section on it later on. I just want to show that up. Why? Because you remember, if you do a square root of something, square root of 4, it should be a plus or minus 2. So technically, every time we do a square root, shouldn't there be another value? The answer is yes, but we actually ignore this portion. What problem do we run into if we decide to add the bottom portion? Anyone want to guess?
Root of a negative number.
Root of a negative, not necessarily, no, I mean, we're doing a root of a positive number, but we end up getting two answers.
Two
And it
values
doesn't
per
pass the vertical line. Yeah, it's no longer a function. That doesn't help us. Remember, the whole point of our learning this math is that if we put in a number, we want a definite answer. We want a single answer if possible. So having two answers sort of defeats the purpose. So when we do square root functions, we automatically assume that we're going to deal with the positive value. So I'm going to put a little square. If we count both plus and minus of a square root, we have two y values, which we don't want. So we ignore the negative side for the purpose of using this as a function. Okay? Just to let you know, we're always going to have this this one-sided curve, okay? We're not going to have both top and bottom together when we do square root functions. Although technically both could exist, we don't want it because it doesn't help us. Okay, last one. Last question. Any questions before I go on? I got 7 minutes with you. All right. If you do have a question, please email me or leave it somewhere in chat, and I will address it. If it's something that I should answer through video because it's more complex, then I will do so. Okay. Reciprocal function. Oof. This one's the hard one. This one's by far one of the more I'm gonna say fun ones. Okay. I'm gonna give you 6 accuracy points. So stay tuned. We've got 1 and 1. Why do we not start with 0? It has a built-in restriction. X can never be a 0. And if this becomes a 2, then I have a 0.5. If the x becomes 0.5, I have a 2. It's sort of like a mirrored version. On the negative side, if I have a negative 1, I get a negative 1. If I have a negative 0.5, I get a negative 2. And if I put a negative 2 in, I get negative 0.5. It's mirrored. Let me show you what that looks like. Looks like this. It's sort of like a bow tie. And it doesn't, and you might wonder, like, where is this going? I don't understand a thing. Like, I don't know where what this is going to look like. But there's going to be 2 more things that are going to help us. You remember this restriction? X cannot be 0. In other words, here is a line when x equals a 0. This line can never, or the curve can never exist at this point. Yeah. So yeah, it's the funny name that I'm going to give. And Kinda's got it. X equals 0 is what we call a vertical asymptote. Yes, asymptote. I know it's a little bit funny. My wife got me a sweater with a joke involving that for a birthday a long time ago. I still have it. Maybe I'll wear it for you. A little inappropriate, but for the sake of humor, maybe I'll wear it for you one day. Okay? Vertical asymptote. In the same way, there's actually another one. There's a horizontal asymptote, and that is when y equals a 0. Why can't y equal a 0? Anyone want to take a guess? Look at the equation, 1 over x. Why can't y equal a 0?
The only way that can happen is by x being equal to 0.
Not quite. Take a look at the numerator. Let's pretend we have x increasing, okay? X is going to approach like a million, okay? What 1 over 10, 1 over 100, 1 over 1,000, as x increases, what happens to the y value? What is 1 divided by 10? Well, I'll tell you, it's 0.1. Who's pretty good with their decimal points? What is 1 divided by 100? Person?
0.01.
0.01, good. And then, if it's divided by another 0?
One more 0.
One more 0, good. And it gets smaller and smaller and smaller the further we go along the x-axis. Here's a question. Will it ever equal 0?
No.
No. Will it get close to 0?
Yes.
But will it equal 0? No. So because of that fact, this function is going to get, and as one of my math teachers back when I was in high school said, infinitesimally close to 0, but will never touch 0. I don't know why he said infinitesimally. That doesn't make any sense, but whatever. I thought it was funny. I always made fun of him and he hated me. Anyways, same with this one. In the negative side, there. This is the reciprocal function. And it comes with two asymptotes. So I'm going to add plus the asymptotes x equals 0 and y equals 0. Okay? So the reciprocal function is by far the most complex one. So that might actually require a little bit of memorizing, but once you draw it again and again and again, you'll realize, oh, it's actually sort of interesting, and the asymptotes really help me guide the lines accordingly. Okay? Number 6 is the cubic function, but if you see it in brackets, I say it will not be evaluated because it's not part of the grade 11 curriculum. I don't know why, it's not that hard, but I mean, I could have just given it to you. Thank you. Right? And as a sort of a farewell for the day, before I see you tomorrow, I want to share with you that if you think that these functions are difficult, you're not alone. Okay? It's to the point where just to help memorize, there are students out. I mean, there have been grade 11 students that came before you. There will be grade 11 students that came after you. Even when I was in high school, this was rotating in the internet. So parent functions dance. So to help them with the parent functions, people made things like this to help them get by. Take a look. Don't worry about sine or cosine or tangent or anything like that, right? Here is the absolute value. It's a yay. Linear function, it's a line, yay. Quadratic, it's a parabola, yay. Square root, it's a dance this way. Reciprocal function, it's a dance this way. Whatever you have to do to make sure you're memorizing it, do it. Okay. There are some others in here. Here's a more rougher example. but I'm hoping that you can see it. You see it? X squared, x cubed. Oh, Miss Jones has center cut. Yeah, no, it helps. If you are a kinesthetic person and you're like doing all the things, it'll help. As we get to chapter 3, chapter 4, and even chapter 5, I'm going to introduce a couple more, like this y equals sine x thing, where the person is doing this little like wave function. If it helps, do it, because that's literally what the curve looks like. All right? And this is what we're going into. We're going to learn all the different parent functions, because if you have the parent functions, all you got to do is know what it looks like to translate it up and down, translate it left and right, and then maybe vertical stretch it and whatnot, and flip it around. Okay? Keep 2.6 in the back burner. Okay? Keep it in your notes. You're going to refer to it when we get to chapter 2. But right now, of course, your priority is do some of the homework for linear quadratic systems, do some of the homework for 1.6, and yeah, get comfortable. Quizzes are out, assignment is out. Remember, the assignment, the rational expressions assignment, is due Thursday midnight. Okay, so if you have to, submit it to me online so that you don't get counted deducted for late marks. Okay? If there are no other questions, I kept you for long enough, you are dismissed. Otherwise, please stick around, leave a question in the chat, and I'll try to refer before we file out. Have a good day. We'll see you tomorrow at 2.
Thank you.
See ya.
Bye.
Thank you. Goodbye.
For everyone else here, I will probably have to close this because staff meeting and teachers have to get together and talk about silly things, because teachers always do that. Good night, Ellen. Hope you have a good rest. I don't know what your time is there, but hang in there.
I had a question about the assignment.
Uh-huh.
So I finished it Friday, but it's like pretty messy. Should I just rewrite it on like a few pages so it could be like organized and all that?
Is it legible? Can I make out the answer
It
and
is.
see
It's just
your work?
like it's not great communication. Some stuff is like just scribbled out and.
Uh, I'll put it this way. I have no problem marking work that is messy. But if I can't follow it, right, then I can only base it on your final answer, right? Like if you
Makes
want to
sense.
if you want to show your work and like I'm not gonna flack on you for being messy because that's not what I'm grading you for. But I should at least be able to follow your brain.
All right,
Okay,
I'll
so
probably just do it anyways.
if you need to just draw arrow, no, like you can draw arrows to help guide me. Do whatever you need to, but as long as I can follow it, that's my only criteria.
All right, thanks.
Okay, all right. I'll see you later. Kira, are you with us?